Carbon nanotubes are rolled up sheets of graphene with amazing mechanical, thermal, and electrical properties.
Well, CNTs are very simple. They are carbon atoms arranged in a molecule form. The black things in here in this model is a carbon atom. The transparent tubings represents carbon bonds, so they form 6-member rings of carbons, and they roll up in a tube like this. And it's one of the bigger molecules you can find.
Today we're going to look at some carbon nanotubes under scanning electron microscope.
Carbon nanotubes are nanocylinders. So then the question would be, what would be the diameter of the nanocylinder?
Now let's load the sample into the SEM chamber.
So typically, for example, for the carbon nanotubes that we grow in our lab, the diameter would be maybe 1.2 up to around maybe 1.5 nanometers.
We'll raise the height to a height that's appropriate for imaging.
For example, if you draw a long line, which is a meter long, and now you split up that line into billion equal parts, the length of one of those parts would be 1 nanometer.
The samples that we'll look at have carbon nanotubes that are single-walled and semiconducting, grown horizontally and in a line fashion. It's a ring of carbon that is 1 to 2 nanometers wide, and it can extend up to 1 millimeter long, so it's 1 million times longer than it is wide. And because of this unique property, they're very useful for applications in electronics.
CNTs are exciting because if you can build transistors and logic and digital systems out of the CNTs, you should be able to produce this really high performance information technology systems. You should be able to run that system out of a tiny little battery.
Yeah, with carbon nanotube, it's a very special material. So we want to use them to make things that are not possible with other materials, or enable new devices or new technologies where nanotube can allow much better performance.
Depending on how a sheet of graphene rolls into a carbon nanocylinder, that determines the electrical properties of that carbon nanotube. Sometimes you could have carbon nanotubes that are semiconducting, which you would use for transistors, or they could be metallic. Those would be terrific for wires, but they are not very good as transistors. When you grow these carbon nanotubes at a very large scale, it's extremely difficult to control that all your carbon nanotubes would be perfectly semiconducting.
I work on demonstrating that we can experimentally build working, larger scale, useful circuits out of carbon nanotube transistors. Carbon nanotube circuits promise both increased energy efficiency and performance. However, there are many obstacles towards realizing a working carbon nanotube circuit. Now, many of these obstacles are inherent with the carbon nanotubes themselves, such as the mispositioned and the metallic carbon nanotubes. Our group here at Stanford has come up with many techniques, some based on how we design the circuits, some based on fabrication techniques, which overcome these inherent imperfections. By overcoming these inherent imperfections, and by developing robust fabrication techniques specifically for carbon nanotubes, we're able to demonstrate for the first time some larger scale useful circuits using carbon nanotubes. Now, I'll show you 2 of the more recent circuits we've built using carbon nanotube transistors. Meet Cedric, the carbon nanotube digital integrated circuit. Cedric is the first computer built entirely using carbon nanotube transistors. Cedric is a very basic computer which runs a basic operating system, which is capable of multitasking. For instance, right now, Cedric is both sorting and counting numbers concurrently. Cedric is composed of tens of thousands of carbon nanotubes, showing that we can actually fabricate carbon nanotube circuits in a scalable and manufacturable manner. And meet Sasha, the Stanford carbon nanotube controlled handshaking robot. Sasha is controlled by circuits fabricated completely using carbon nanotube transistors, and is the first complete subsystem built entirely using carbon nanotube FETs. Now, let's take a look and see how these carbon nanotube transistor circuits are made. It all begins in this lab, where we grow our highly aligned carbon nanotubes on our quartz wafers. We put the quartz wafer into the furnace, and after several hours, get our grown carbon nanotubes.
then you pass or flow gases that contain carbon atoms, such as methane and so on. And on the substrate, you would put catalysts, such as iron or cobalt, metal catalysts, and carbon nanotubes would then grow from these catalysts, getting carbon from the environment where you feed the carbon gas in.
After growing the carbon nanotubes on the quartz substrate, we then transfer these carbon nanotubes onto a traditional silicon dioxide substrate using a low-temperature transfer process. This renders the entire process silicon CMOS compatible.
We have also been able to demonstrate in our group monolithically integrated three-dimensional circuits using carbon nanotube field effect transistors. Now, it's very difficult to build such monolithic 3D integrated circuits using silicon transistors, because once you fabricate silicon transistors in the upper layers, the circuits in the lower layers, they could get damaged. But with carbon nanotube field effect transistors, it's very cool that in the lab, you can build these three-dimensional integrated circuits very easily. And that opens up great opportunities for new generations of circuits and systems that can perform massive amounts of computation in an energy-efficient manner.
And I'm building a skyscraper in the world of carbon nanotubes. Think of one single transistor as one person. Today's integrated circuits are like the Quincy Market in Boston, where all the vendors and customers are crowded into one single story, and it can be extremely difficult for you to move from one end to another. We can make tomorrow's electronic systems skyscrapers where we have multiple stories on top of each other, so that more people can work together and collaborate more effectively. While people are trying really hard to push the physical limits of the transistor scaling, carbon nanotube 3D integrated circuits manifest themselves as a brand new interpretation of the traditional concept of scaling.
These circuit designs are so efficient that at a large digital system level, there is almost no additional costs in terms of power, performance, energy, or area that you have to incur to be able to create these systems that are immune to these inherent imperfections at the carbon nanotube level. And that's where there are opportunities for great innovations that we are working on.